Hello and welcome back to my YouTube channel. We want to continue from where we left in our last session, and if you can remember, this is what we learned in our last session. So we were able to calculate loadings on this beam on grid line 2, which is this beam, and this was our finding values, whereby GK is equal to 44.41 kilonewton per meter, and the QK was or is 10.5 kilonewton per meter. And therefore, from our calculation, we were able to see whether we can design this continuous beam using the special method or we use the rigorous analysis method, so that we can analyze the beam and therefore we design the beam. So for the special method, the condition given in Eurocode 2, it was not met by this beam. Number one, the GK must be greater than QK, which is okay. And number two, the spanning of this beam or the spanning of the beam must have 3 and above. As you can see, we have 1, 2, 3. Therefore, it meets the condition. The condition number 3, it is that the difference in length variation or in spans variation must not be greater than 15%. And we were able to see that the smaller span is 3 meters and the bigger span is 4 meters. Therefore, the variation between 3 and 4, it is 25, or it was 25. Therefore, it disqualifies the special method for the design of this beam. And therefore, we decided to go with the rigorous analysis. So today, we want now to proceed with this analysis of this beam. And remember, we calculated the design ultimate load, which we find that it was 75.70 kilonewton per meter. So we want now today to analyze this beam using moment distribution method, and henceforth we will design the beam as per the bending moment diagram and shear force diagram that we will achieve from analysis of this beam. So stay tuned as I start up to the end. And due to lack of space, I want to clean everything on this board so that you can have enough space for our calculation. But for this plan, I want to attach it on the left side of your screen. It will be on this side, so that we may be referring as we continue with our calculation. So this is the beam. As you can see, it is a continuous beam which has a UDL of 75.70 kilonewton per meter. So very important things to note on this beam. As you can see, the end supports are simple. So we will assume our end support is simple, or a simple connection. But for the purpose of construction, when doing the analysis before design, you are supposed to analyze using 2 different end conditions. For example, for this case, we are supposed to begin by assuming our end support is simply supported, and then we carry out the analysis and draw the shear force and bending moment diagram. And then the second one is to assume these end supports are fixed. Fixed, it means it is permanently fixed. And then we carry out the analysis, come out with the shear force and bending moment diagram. And then after that, we compare the two. The one that will give the worst result. The worst result means the one with the highest bending moment is the one we will use for the design purposes. But due to lack of time, let's assume these 2 end supports are simple supports. And something again to do before you start analyzing this beam is to decide the I. The I is the second moment of area. So in Eurocode 2, it allows a constant I if the variation in span is too small. Too small, it means there is no bigger variation. For example, in our case here, we can assume our I is constant. So this one will be I, again this one I, again this one I. Remember, I is very important when it comes to moment distribution method or even three moment, because it will help us in calculating the stiffness factors for this beam. And if the variation is so big, then it means you have to calculate the I. For this case, I have already proven that I is constant by doing my own calculation, which I will not include in this because it will take a lot of time. As I have said, the Eurocode allows to use I constant if the variation is too small. Again, I have already calculated the I to prove it is constant, but I will not show you how I have done it because it will take a lot of time. So to calculate I, if the variation is very big, for example, here, let's say here is 1.5, and then here is 3, and then here is 4.5. That variation is very big, which means you have to calculate the I. So to calculate I, first you have to calculate the BEFF, which is the flange breadth or the effective flange breadth for these spans. Therefore, after calculating the effective width flange, you come up with a section. I'm just demonstrating in case the variation is very big, such that this is HF, which is 150, and this is the depth of the beam, which is 450. This is from our previous information, and here is BEFF. So you have to find the I for this. This is for span number 1. If the variation is so big, so you have to find the variation for this, and then you come to this number 2, span number 2. Again, you do the same. The BEFF, which is the effective flange width, is different. So again, you have to calculate the BEFF, come up with your shape. It is T because this beam, it is supporting slab on the left side and on the right side. So again, this will be 150, here 450. And then here is BEFF number 2. This is number 1. And then you calculate, this is, let's say I number 1. And this one will be I number 2. You will do the same to this. So this is now span number 3. You calculate BEFF number 3, which is the effective flange width. And then you come up with your section. So this is number 3. And then here is 150. And here is 450. And then you calculate I3. After doing so, for example, let's say I1 is equal to 8.0 times 10 raised to power 9. And then I2 is equal to, let's say, 6.2 I2 times 10 to the power of 9, and then I3 is equal to 12 times 10 to the power of 9. Remember, this is millimeter to the power of 4, millimeter to the power of 4, millimeter to the power of 4. I for analysis is equal to 0.35 times I gross. These are the I gross. These are the I gross. So you will multiply 0.3 times this, times this, times this. Let's say if you multiply 8 times 8.0 times 10 to the power 9 times 0.3. Let's do it practically. So 8 times 0.35, you will get 2.8 times 10 this power of 9. So this is I1 for analysis. And then I2, you will take 6.2 times 0.35. So you'll get 2.17 times 10 times 10 raised to power 9. So this is I2. And then we proceed to I3. We will have 12 times 0.35. So this is 4.2 times 10 raised to power 9. So this is I3. And then what you do, take the smallest value, which is 2.17, and divide it by the rest. Divide first by itself, which will be I, or 1I. And then take 2.8, divide it by 2.17. So here again you will have 1.2. Let's say 1. Or let's just round it to 1. So this is I again. And then we take 4.2 divided by 2.17. So this one will be 2I. So in your beam, you will have I, then I again, then 2I. So that is how you come up with I. But since for our case, as I have said, the variation is very small, let's use I constant. So let's proceed. Solution. The first thing to do is to start calculating fixed end moment. Fixed end moment. And we will begin by span. Let's begin with span. Now we assume the ends of this support are fixed. So we begin with span 2A to B. Like that. So this is 3.5 meters. This is 2A and this is 2B. So this is our fixed end moment. Again, this one is our fixed end moment. So this is ME, fixed end moment 2AB. 2A to B, and this one is fixed end moment 2B to A. So fixed end moment 2A to B is equal to minus WL square all over 12, because this is moving in anti-clockwise direction. So the W here is the loading on this beam, which is 75.70 kilonewton per meter. So this one is equal to minus 75.70 times 3.5 square all over 12. So minus 75.70 times 3.5 square over 12 is equal to minus 77.28 kilonewton meter. So this is fixed end moment 2A to B. And then we move to fixed end moment. Fixed end moment. This one 2B, 2B, 2A. So this one is equal to WL square over 12. This is positive. This is positive because it is moving in clockwise direction. Therefore, the figures remain the same. What it changes here is sign. So you just say plus 77.28 kilonewton meter to avoid a lot of calculation. So we come to span. We come to span this one now to C, no, to B, and then to C. So this is the span. Let's draw it here. So this is the span. And this is 3.0 meters. This is 2B. And here is 2C. And then fixed end moment, fixed end moment. So this is fixed end moment 2B, 2C. And here, fixed end moment 2C, 2B. Like that. So fixed end moment is equal to, we begin with this one, fixed end moment 2B, 2C. This one, it is in the direction of anti-clockwise. So minus WL square all over 12. So this one is equal to, this one is 75.70 kilonewton per meter. So the W is 75.70 times 3 square all over 12. Remember, it's negative. So this one will give us equal to negative 56.78 kilonewton meter. And then we proceed to fixed end moment 2C, 2B. This one here, 2C, 2B, it is in the direction of clockwise, plus WL square all over 12. So the values remain the same. What will change is the sign. So just say plus 56.78 kilonewton meter. We proceed to span 2C, 2D. Span 2C, 2D. So let's draw it here. Here is 75.70 and then 4 meters. So this is fixed end moment. This is 2D. This is 2C. Fixed end moment 2D, 2C. Again, we have fixed end moment here, which is 2C, 2D. Like that. So we begin by fixed end moment. This is 2C, 2D. Because it is in the anti-clockwise direction, the formula will be minus WL square all over 12. So this one is equal to negative 75.70 times 4 square all over 12. So this one will be, let's carry out the operation. So this is negative 100.93 kilonewton meter. Then we proceed to fixed end moment 2D 2C. So this one is equal to positive WL square all over 12. So the answer will remain the same. The sign will change. So this one will be positive 100.93 kilonewton meter. So we are done with fixed end moments. So the next step is to calculate stiffness factors. And before I can clean the board, I want you to write this somewhere. This fixed end moment, because we'll use them in our proceeding calculation. So write them somewhere. And this. So we now proceed to stiffness factors, which is K. So for stiffness factor, we have various formula which are used to calculate these stiffness factors. For example, for a simply supported beam or a pinned or overhanging, K is equal to 3 over 4 I over L, or 3 EI all over L. We proceed to fixed or continuous beam or beams. So this one, K is equal to I over L or 4 EI over L. So these are the formulas to use when calculating stiffness factors. So something very important to note, do not try to prove your answers while doing your calculation by using these two formulas. These two formulas will not give you the same value for stiffness factors. But when it comes to distribution factors, these two, the values obtained by these two formulas, it must result into the same distribution factors. So that point is very important. So let's proceed now to K. We start with span 2A to B. So this one will be K 2A to B. So something that is very important when calculating K, use the farthest support. For example, the farthest support from 2A to B is this 2A, or this is the end support. So the end support, as you can see, is pinned, or is a simple support. Therefore, we'll use this formula, 3 over 4 times I over L, which is equal to 3 over 4 times I. I is 1. All over L is 3.5. So this one is equal to 3 over 4 times 1 over 3.5. So this one is 3 over 14. So that is K 2A 2B. We proceed to K. Now we are here. 2B to C. As you can see, the farthest support is a continuous. This is a continuous support. So therefore, we use I over L. So this one is equal to, what is I? I is 1. And what is L? L is 3. Like that. And then you proceed to K. You are now here. 2C, 2D. So the farthest or the end support is a simple support. Therefore, use 3 over 4 times I over L times I over L. So this one is equal to 3 over 4 times 1 over 4, which is equal to 3 over 16. 3 over 16. We now proceed to distribution factors. So for distribution factors, let's begin by joint A. Joint 2A, not A. So for joint 2A, we have DF 2A 2B, which is equal to 1 because it is a simple support. And then we proceed to joint 2B. So for joint 2B, we have DF 2B 2A. So this one is equal to K 2A 2B all over K 2A 2B plus 2B K 2B 2C. So this one is equal to K2A 2B. K2A 2B is 3 over 14 all over 3 over 14 plus K2B K2B to C. K2B to C is a third plus a third. So this one is equal to 3 over 14 all over 3 over 14 plus a third. So this is 9 all over 23. We proceed to K under the same joint 2B. We now proceed to DF. We now proceed to distribution factor 2B to C. Here 2B to C. So this one will be K 2B to C all over K 2B to C plus K 2A to B. So this one is equal to K2B to C is here all over third plus 3 over 14. So this one is equal to 14 over 23. And remember, If you add the distribution factor at adjoint, it should give you 1. So add this to this one, it is supposed to give you 1. If not 1, then you have committed an error somewhere, so you have to repeat. So we proceed to joint. We now proceed to joint 2C. Joint 2C, we have DF. We have DF 2C 2B. So this one is equal to K 2C 2B over K 2C 2B plus K 2C 2D. K 2C 2B over K 2C 2B plus K 2C 2D. So this one is equal to a third all over a third plus 3 over 16. So this is 1 over 3 plus 3 over 16. So this is 16 all over 25. So let me clean here so that you can continue. So under the similar joint, which is joint 2C, we have DF 2C 2D. So this one is equal to K 2C 2D all over K 2C 2D plus K 2B 2C. So this one is equal to 3 over 16 all over 3 over 16 plus a third. 3 over 16 all over 3 over 16 plus a third. So this is 9 over 25. Again, 9 over 25 plus 16 over 25 supposed to give you 1. That is the total distribution at the joint. We proceed to joint 2D. So joint 2D only have DF 2D 2C, which is equal to 1 because it is a simply supported, or is a simple beam. So this one is equal to 1. So those are the calculation of distribution factors, and we now proceed to table. Let's now proceed to table. This is the distribution table, and this is our continuous beam. So we start by joint. Joint, we have joint, which is 2A. Under joint 2A, we have member. We have member 2A, 2B, and then we have joint 2B. This is joint 2B. So for joint 2B, we have member 2B2A, 2B2A, and member 2B2C, 2B2C. And then you come to joint 2C. Joint 2C, you have member 2C2B, 2C2B, and member 2C2D, 2C2D. And then you come to joint 2D, we have member 2D2C, this member. So like that. And then we come to distribution factor. We have already calculated this. and just pick the values and write where they belong. And then again, we come to fixed end moment. We already have this again, so you just pick them and write to their respective column. And then after that, we now start working on the values. Remember, this is now our, as from here to this, we are now calculating our moment, or we want now to start working on our values. So the first step to do is to check whether your end support is either fixed, simply supported, or overhanging. So for our case, the end support is a simple support. It means for a simple support, the end moment, it has to be 0. It has to be 0. But as you can see here, this end moment is not equal to 0. So for this 2A, 2B, and this 2D, 2C is not equal to 0. So what are we supposed to do? What we are supposed to do is to release. We release this fixed end moment so that if you add the two, this one and this one, it should give you 0. And to release, you just use the same values, which is fixed end moment, and change the sign of that value. For example, here we have negative 77.28. So if we change the sign and we maintain the value, it will be positive 77.28. The same apply to this, positive 100.93. So change the sign, which is positive, it will be negative, and you maintain the value. So such that if you add this, you get 0. And also if you add this, you get 0. Now we have balanced, or we have released joint 2A and 2D. And then what follows next is to carry over. Immediately after you have released or you have balanced, you are supposed to carry over a half of the value here to the next opposite member. So the next opposite member is 2B, 2A. So a half of 77.28 is 38.64. And then a half of negative 100.93 is negative 50.465. Remember, when you carry over, or when carrying over, you carry a half of that values, or of that value you have balanced. And that value, it includes the sign in front of that value. So you carry a half of everything, including the sign. And then after doing so, we now calculate the initial. This is initial final moment. So initial final moment is the sum from fixed end moment to carry over. So this one plus this one is 0. This one plus this one, you get 115.92. Negative 56, it will come here, this the way it is. This one, it will come here the way it is. Negative 100.93 plus minus 50.465, you will get negative 151.395, and then positive 100.93 plus minus 100.93, you will get 0. So we are now at, we want now to start again working from initial final moment as we proceed to the final value. So now from initial final moment, we now start balancing and carrying over. So to balance, it means a joint which is at the center, like this one and this one, they are a simple supports. So simple supports, it means the fixed end moment in that joint, it has to give you, if you add, it should give you 0. For example, 2B, we have member 2B, 2A, and 2B, 2C. So if we come here and add this to this, it should give you 0. But if it's not equal to 0, then it means you are supposed to balance. Let's do it practically. So it is 115.92 plus minus 56.78. So the answer is positive 59.14. Now to balance, change the sign of this value you have obtained, which is 59.14 is positive. Now it will be negative 59.14, and distribute it equally to each member by multiplying the value with the distribution factor. For example, negative 59.14 times 9 over 23. So this is negative 23.1417. You do this, you repeat the same to member 2B, 2C, you'll get negative 35.998. And then you proceed to 2C. Again, you'll take positive 56.78 plus minus 151.395 and see whether it is 0. So if it is not equal to 0, then that member is not balanced. Therefore, you have to balance. So 56.78 plus minus 151.395. This one is negative 94.615. So you'll take positive 94. Let me do it again. 56.78 plus minus 151.395. So you get negative 94.615. So this one will be positive 94.615, and then distribute it equally to each of this member. So take the answer, which is positive 94.615 times 16 over 25. You'll get 60.5536, and then come here, again multiply the same value by 9 over 25. By 9 over 25, you will get 34.0616. And then after here, you have to carry over. After every balancing, you have to carry over. Carry over, it means you carry a half of this, a half of the balanced value to the opposite member. As you can see, this 2B, 2A is opposite to 2A, 2B, but you cannot carry over this 23.1417 to this member, which is 2A, 2B, because you have already obtained or balanced this member 2A, 2B, and our initial final moment is 0. So we are not supposed again to carry over to this member. So we will come again to this one. We are not supposed to carry over a half of this to this member because we have already obtained 0. So carry a half of this 2B, 2C to 2C, 2B, and then 2C, 2B to 2B, 2C. These are two opposite members. So you carry half of this to this, half of this to this. So if you take negative 35.998 and divide it by 2, you will get negative 17.999. Again, if you take positive 60.5536, divide it by 2, you will get 30.2768. And then after that, you can now again balance. So to balance it means take opposite of 30.2768. This is positive. So positive 30.2768 is negative 30.2768. Multiply that negative 30.2768 by distribution factor for each member. So for example, negative 30.2768 times 9 over 23. 9 over 23. So you get negative 11.8474. And then again you take negative 30.2768, multiply it by 14 over 23. You'll get negative 18.4294. Again to this one, take positive 17.99 times 16 over 25. You will get 11.5194. Again, take positive 17.999 multiply by 9 over 25. You will get 6.4796. After that, you carry over half of this to the opposite member, half of this to the opposite member. You will repeat the procedure. You repeat the procedure until you arrive on a carryover which has a value of 0.0. You have to reach at a point where carryover is 0.0 to something. And then from there, you can have your final moment. So this is the continuation of this table, but I have skipped this column for 2A and column for 2D because their moments are 0. So I picked 2B, this is joint 2B and 2C, 2B and 2C, and this is their members. So this is the continuation. So here is carryover, which is 0.561 and negative 0.8975. So to continue, you have to balance this. So take opposite of 0.561, which is negative 0.561 times 9 over 25. 9 over 23, not 25. You will get negative 0.2195. So again, multiply it the same value by 14 over 23. You will get negative 0.3415. The same apply to this one. This one will be positive 0.8975 multiplied by 16 over 25. You will get this one. Again, positive 0.8775 multiplied by 9 over 23. You will get this one. Carry over. Repeat until you come to where the carryover is 0.00 something. You can even continue from here. But let's stop at carryover at this juncture, which carryover is 0.0547 and negative 0.0874. And then you have the final moment. For this 2B2A is 0, so no need to include in this column as I have said. Again, for this one, it will be 0. So we will be calculating 2B2A. So you add from here, from initial final moment, which is 115.92 plus negative 23.1417 up to this point, and then you come add this one, you'll get 77. I have rounded it to the whole number. Again, you come to 2B2C. From initial final moment, take negative 56.78, add negative 35.998, add the rest up to this point. Come include this one, this one. You'll get negative 77. Repeat to the other columns or to the other members, which is 2C and 2D. This is 2C, 2B. We start from here. Positive 56.78. Add all of these up to this point, and then come include this one. You'll get positive 106. The same to this one. From initial final moment, negative 151.395. Add. add, and then you will get negative 106. So from there, you can now calculate the reactions at the supports. After calculating the reactions, we will now be able to draw the shear force and bending moment diagram, which will help us in designing the beam. So allow me to clean, but you can write this somewhere. 77, negative 77, 106, 106. Remember also this one to include 0 and 0 for the member 2D, 2C, and 2A, 2B. We want now to calculate the reactions for this continuous beam. And to calculate the reaction for this continuous beam, where we have a common joints like 2B and 2C, we'll break them into two or split them into two. For example, at 2B, we'll have R2B1 and R2B2. And then for 2C, we'll have RC1 and RC2. But where we have only a single a joint which is not common, so we'll only have R2D, like for this case, and R2A for that case. And then we have the moments. We have already calculated the moments at this joint. This is at joint B, at joint 2B. At joint 2B, as you can see, it's 77. 77, so it can be either positive or negative depending on the direction of the moment. Again, for this case, which is joint 2C, we will have 106. It is here. It can be either positive or negative, depending on the direction of the movement of that moment. And for joint 2D and 2A, it will be 0. That one is equal to 0 because it is a simple supports. So we now proceed to the calculation. Again, remember the spanning lengths, which is 3.5, 3.0, and then 4.0, like that, 3.5, 3.0, and 4.0 meters. And then the loading, of course, is 75.70 kilonewton per meter. We now proceed to the calculations. And for the calculations, we'll start by calculating the reactions for this, a simple beam, this one. Remember, we have splitted the beam into a simpler beam. We now begin. So summation of moment at R2A is equal to 0. We are at this point. Now, if we sum moment at R2A, we will automatically be calculating the moment for, the reaction for R2B1. So this reaction is moving in anti-clockwise direction. So you take negative 3.5 R2B1. It is negative because it is moving in anti-clockwise direction in reference to this point. And then the distance from this point to this is 3.5. And then you come to UDL. This is the UDL. As you can see, it is moving in clockwise direction because it starts here and it ends here. So this is plus 75.7 times 3.5. Change it to UDL times 3.5 all over 2. Remember, the moment for a UDL, it acts at the center of the distance covered by UDL. And then you come to this moment here, which is 77. In which direction is moving? This direction. So this is positive because it is clockwise direction. Plus 77, then you equate to 0. So which imply R2B1 is equal to, and then we come to 2RA. This one will be equals to 75.70 times 3.5, change it to a point load, then minus. This is because summation of upward forces is equal to summation of downward forces. So the upward forces is R2A and R2B1. And then the downward forces is 75.70 multiplied by 3.5. So this one will be equal to Newton. That is 2RA. We now proceed to this. We are done with this one. We proceed to this one. Again, summation of moment at RB2 R2. This should be R2B2. R2B2 is equal to 0. And this one should be R2C1, R2C2, R2TD, like that. So this one will be moving in anti-clockwise direction, which is negative 3, sorry, R2C1 plus the UDL, which is moving in clockwise direction, plus 75.7 times 3, then times 3 over 2, because it acts at the center. Then we come to the moment. We start with this one, 77, it is in the anti-clockwise direction, so this is minus 77. And then 106, it is in clockwise direction. And then you find your answer. So this one is equal to 0, which imply R2C1 is equal to 75.7 times 3 times 1.5 minus 77 plus 106 divided by 3. So this is 123.22 kilonewton. And then for R2B2 is equal to 75.7 times 3 minus 123.22. 75.7 times 3 minus 123.22. So this is 103.88 kilonewton. We proceed to the last span, summation of moment at R2C. No, we have not calculated the reaction for yes, we are okay. Summation of moment. We proceed to this one. Summation of moment at R2C2 is equal to 0. And then you have negative 4 times R2D, then plus the UDL, 75.7 times 4 over 2. Then minus 106, because it is moving in clockwise, in anti-clockwise direction, plus 0, no need, is equal to 0, which imply, let me write it here, which imply R2B2 is equal to 75.7 times 4 times 2 minus 106 divided by 4. So this is 124.9 kilonewton. And then R2C2 is equal to 75.70 times 4 minus 124.9. So the reason remains the same. Summation of upward forces is equal to summation of downward forces. 75.7 times 4 minus 124.9. So this is 177.9 kilonewton. So those are the reactions. This is how you draw a shear force diagram. We have already calculated reaction 2A, and then reaction 2B is the summation of reaction 2B1 plus R2B2. So you'll get 258.36 kilonewton. And then for R2C is equal to R2C1 plus R2C2. You'll get 301.12 kilonewton. Now, this is the shear force diagram, and this is the bending moment diagram. So this is the neutral line. Above this line is positive, below is negative. And for the bending moment, above is negative, below is positive. Now we begin with reaction A. Reaction A is 110.47. So you approximate, let's say somewhere here. This is 110.47, like that. And then you take your calculator, 110.47 minus the UDL on the beam, which is 75.70. Change it from UDL to point load, multiply it by 3.5 times 3.5. So you will get negative 154.48. Negative 154.48. So approximate, we approximate like there. Yes, there 154.48. And then for the UDL, it is an inclined line, like that. Then take this negative 154.48 plus reaction at B, which is 258.36. You'll get 103.88. Approximate like there, 103.88. Again minus the UDL, which is 75.70 times 3. Change UDL to a point load. So you will get negative 123.22, around there. So negative 123.22. And then you add reaction at R2C plus 301.12, which is 177.9. 177.9, like there, 177.9. Yes. Again minus 75.70 times 4. 124.9. 124.9. And then you add reaction at R2C to D, which is 124.9. I forget to include there. So take this minus 124.9, add 124.9, you'll go back to 0. So this one is positive, negative, positive, negative, positive, negative. So that is the shear force diagram for our beam. Like that. So after drawing the shear force diagram, it is very important to note where the shear force changes sign from positive to negative or from negative to positive. That is where the shear force value is 0. So it is at this point. So at this point, we will have maximum bending moment for this section. Again, we have this point where the shear force is changing sign from positive to negative. I have marked the point and also this point. So this point again will have the maximum bending moment for this span. And then you come to this one. This is the point where the shear force is changing sign from positive to negative. At this point, we will have a maximum bending moment. So if we can label this point, let's call this point X. So this one will be 3.5 minus X. We come to this one. Let's call this one X1. So this one will be 3 minus X1. We come to this one. Let's call this one X2. So this one will be 4 minus X2. So this is how you calculate the values for X. You can use similar triangles. For this triangle, we compare with this one. So we'll have 110.47. This is the height, and then over 3.5 minus X is equal to this height from here to here, 154.48 over X. Then you cross multiply, which imply X is equal to 154.48 times 3.5 divided by 110.47 plus 154.48. So X is equal to 2.04, which is here, 2.04 meters. And then here is 3.5 minus 2.04. 3.5 minus 2.04, which is 1.46 meters. 1.46 meters. So 1.46 meters, like that. So, and then we proceed to the other spans. Again, we come to this one. We compare from here to here, which is 103.88. This is 103.88 over X1 is equal to 123.22 over 3 minus X1, which imply X1 is equal to, remember this is X, which imply X is equal to, X1 is equal to 103.88 times 3 divided by 123.22 plus 103.88. So this is 1.37. So here is 1.37, 1.37 meters. And then 3 minus 1.37, this one is 1.63 meters. We come to the last one. This side from here to here is 177.9 all over x2 is equal to 124.9 all over 4 minus x2, which imply x2 is equal to 177.9 times 4 divided by 177.9 plus 124.9. So this is 2.35 meters. So this is 2.35. And then 4 minus 2.35, this is 1.65 meters. After that, we now proceed to the bending moment diagram. We can now calculate the bending moment values. So for this point is 0, and then we'll come at this point, at this line. At this line, the bending moment will be the area of this shaded part or a shape, which is a half base times height. So 0.5 times 110.47 times base, which is 1.46. 1.46. So this is 80.64, which is positive. Around there, 80.64. And then we come to this point at this line, which is 2B. So here, you will take this one, this 80.64 minus the area of this shaded part, which is on the negative side. So this is 0.5 times 154.48 times 2.04. So you get negative 76.93 around there, 76.93. After that, we come at this line. So you will add 76.93, which is negative, plus the area of this shaded shape, which is a half, 0.5, times base from here to here, which is 1.37, times height, which is 103.88. So this is negative 5.76. Negative 5.77. Like that. So here, let's use 77 because it has to be the same from the one we calculated. So let's round it to the whole number and make it 77. So here it will be 77, negative 77 minus 0.5 times 1.37 times 103.88. This is plus, not minus. Let's repeat. Negative 77 plus the area of this shaded part, which is a half, 0.5, times base 1.37 times 103.88. So this is negative 5.84. 5.84, like that. $5.84. After obtaining this negative 5.84, subtract this area, which is minus 0.5 times 123.22 times the base 1.63. So you get negative 106. So negative 106 is somewhere here. 106. And then from there, add this area so that you can have your B.M.D on this line, on this zero shear force. So plus 0.5 times H is 177.9 times the base 2.35. So you get positive 102.77. 102.77. And then here will be 0. You can prove it. This is positive minus this area. Just say minus 0.5 times 124.9 times 1.65. Automatically is 0. So you can now join these points with a smooth circular curve like this one. So this one is positive, negative, positive. Like that. So we will use this maximum bending moment at each spans and support to design our beam. So in our next session, we will design this beam based on what we have calculated, and I think I will end there. And thank you for your time, and thank you for watching this video. For those who have not subscribed to the channel, please subscribe and hit the notification bell so that will be the first person to be notified. So let's meet in our next session so that we can continue with this Example,